we have Andreas Pflitsch and his graduate student Annika Gomell, and I do hope I pronounce those correctly. Andreas is a geographer and climatologist based at the Ruhr-University in Bochum, Germany, who has been studying micro and climatological processes in caves for over 20 years. He started this work in Poland in 1997 and then started working on similar studies in wind and jewel caves in South Dakota in 2002. In 2008, he also began working on airflow projects in Carlsbad Caverns National Park, doing climate studies to determine whether the caves in the park might be connected. Since then, Andreas has expanded his research in the USA to include ice caves in various states, lava caves in Hawaii, and glaziovolcanic caves in the Pacific Northwest, as well as copper mines in Alaska. Annika is a Ph.D. student in climatology, working with Andreas at Ruhr-University. Her research studies have included research inside Wind Cave, Jewel Cave, and the caves of Carlsbad Caverns National Park. Her research is focused on air pressure propagation and airflow systems inside the caves. Thank you.
Yeah, thank you very much, Hazel, and good morning to everyone. And I hope you can see my presentation and can hear me well. Yes, we have a divided presentation. So I will talk a little bit about the first research I've done in Carlsbad Caverns National Park, and Annika will present the latest research we have done, or she has done in the park. So I'm here for the old stuff, Annika is here for the new stuff. And so this is one of my very first presentations I gave in the park about the climatological studies I did. So we did a lot of stuff, but I'm focused today more of the size of the caves and are they connected or not connected. And so this is one of my very first thermal pictures I did in the cave, and this is in the winter season more, and you look from the cold outside to the deeper cave, and you see the cave is warmer and you see some tourists walking down. So in my presentation will be about the temperature and not about airflow, not about pressure, but I will explain you why I do just the temperature study right here. So, and I got a lot of help from Stan, John, Gopher, Dale, Paul, and David, and I think most of you know most of these people, and my thanks still go over because without them I couldn't have done all the studies. But let's go to the topic. So in Wind and Jewel Cave in South Dakota, we did some work, and we could find out that most of the blowholes are connected to the big caves, and we could expand at least climatologically the caves much further out. So even when you haven't crawled through the other parts of the cave yet, but we know now Wind and Jewel are much bigger than we thought it about 20 years ago. So and let's have a look here to Carlsbad Caverns, to Spider Cave, and then to Lechuguilla Cave, the big manhole, and even at the other side of the Black Canyon to various blowholes. So the question was, might they be connected or not? So let's start in Carlsbad Cavern, and because we started here with the first measurements, and have a look to the first research area. It was the Devil's Spring area, very close to the natural entrance, and then at the mid-level, the left-hand tunnel area here, this part of the cave. And the Devil's Spring, we put out two data loggers. So one was here at the lower part, close to the pathway for the tourists, and the other one was at the highest level we could go to, and put a data logger very close to the ceiling to see what's going on with the cold air invading the cave in the winter. Do we have a hot ceiling? Whatever. So, and here are the first results. And what you see at the first is the left-hand tunnel data are showing it's really straight, it's more or less a straight line with some variations, and it's much warmer down in the cave than it is at the Devil Springs. Here you see the ceiling, and here you see down at the ground the lower level, and the temperature varies here between 6-7 degrees Celsius in the winter and going up here at the ceiling close to 14 degrees, and here we are much higher. So we are here just a bit below 20 degrees, it's about 18 degrees. So these were the first results, and having a look to the thermal picture, we see really two climate zones. This is a Devil Spring area. Again, here is located the lower data logger and close to the ceiling, the higher one. And you see the ceiling area and the upper walls are much warmer than the lower part of this of the cave right here. And you see this really nice looking line. And most of you, I think, know what this line is. This is the popcorn line. You see really the warm and I can say moist climate here and the cold and drier climate here. So now I have to make a short digression. So how temperature measurements give us some information about the airflow conditions. And this was actually my main purpose of the study. And this is a graph from SNG Cave in South Dakota and the Black Hills. And you see here, this is the airflow axis, and you see here the zero line. And everything what's below the zero line with minus numbers means this is the inflow into the cave. And the blue graph shows you the wind speed or the velocity, and this is the direction. This means an inflow, and everything that's above the zero line, this is an outflow of the cave. And what you can really nicely see, the outflow right here, every time has a really, really clear and clear temperature signal. This is the stable cave air with more or less the same temperature level. And here again, this is an outflow, stable temperature level. And as soon as we have an inflow, we have the daily temperature variation out of the cave. And this is the air moving into the cave. So outflow, stable, inflow, unstable temperature signal. And when we go back to this, we see this is unstable and this is very stable right here. So, but this is not a barometric signal. So, because this is just the summer warming, and you see on the ground and at the ceiling, we have a really slow summer warming, but we have no in or outflow signal. In the winter, we have a clear inflow signal. But this is not an outflow signal. This is just the slow warming till we have the next cold air coming in during the winter month. And so we have cold air breaking into the cave, but we have not a clear signal of any barometric activity. When we go to the left-hand tunnel, this is a little bit different. So we have no real winter and summer signal, but here in the winter, it's a little bit wider space here between the up and downs. And interestingly, the up and downs of the temperature, so the variation is here a little bit higher than here. This means we have a signal what we don't have at the entrance area. And that made me a little bit suspicious. So what do we have at the left-hand tunnel? So, and going a little bit closer to this data, and what I did, I spread here the axis, the Y2 axis of the left-hand tunnel. So here we have 17 to 19 degrees Celsius, while we have here 9 to 14 degrees Celsius for the Devil Spring data. And you see, this is a signal which is very different for this period of just 30 days in November 2009. So very different to the Devil Spring. We don't see really clearly the cold air flowing into the cave at the left-hand tunnel. We have something else. We have up and downs. We have little up and downs, and Annika will tell you what these up and downs mean later. But this is a very different signal. Okay, so we could say we have something which is definitely not barometric, but we have a signal. This could be barometric or maybe something else. Let's go over to Spider Cave, which is pretty close to Carlsbad Caverns. And this is a left-hand tunnel signal. And you have the same range of data. You have the 18th of April 2009 to the 18th of June 2010. And you see this left-hand tunnel signal, really no big variation, still the small variations here, what we talked about before. And the Spider Cave signal, and this is a data logger for temperature just laying close to the entrance area, is very different to the left-hand tunnel, it looks like at least, and then very different to Carlsbad Caverns, because we don't have this slow warming of the summer. We have an up and down, which is typically for barometric caves. But then let's have a deeper look in the data. Just go for a few days and then expanding again the left-hand temperature to just a smaller range of temperature range here, and look to the pattern of the two caves, and you see the left-hand tunnel pattern, and just look to the pattern, not to the real temperature. It's more or less the same. It's really matching well. So the left-hand tunnel pattern to the Spider Cave pattern. So we have more variations here, but we are much closer to the entrance here. At the left-hand tunnels, we are very deep in the cave, and so we have a smoothened signal. So there is something going on, and we know the Spider Cave is barometric. Let's go to Lechuguilla Cave, and here we have the airlock, which makes a very different situation. And we did some temperature measurements as well in the beginning. And you see, have an overview for the first measurements right here. So we have outside of the airlock, we have a very sensitive temperature measurement device, the sensor here. And then inside, behind the airlock, it's called the toilet bowl. And this is really very close to the end of the metal tunnel. When you go down the airlock and you leave, you are squeezed out of the tunnel, and before you have the first drop, here's a location, and some of you have seen this data logger maybe for a few years. And then we have the lower pit, and this is definitely not affected by the barometric airflow. And here you see the data logger on the ground as well. And so these are the results from this measurement. This is from 20th of April 2009 to end of December 2009. We have spring, summer, and winter data. And you see this is a signal like we have seen it in Carlsbad Cavern at the Devil Spring area. Very smooth warming up. And this is a lower pit, definitely not barometric. And then we see here the inside data, inside behind the airlock, inside the cave, and this is in the rock pile in front of the cave. And you see the temperature signal matches really well. And we have definitely a barometric system here, and it's getting much colder air in the winter than it has in the summer. So when you see a higher temperature variation here outside the cave than it's inside the cave, but really much, a lot of barometric signal here. And this is a proof Lechuguilla is a barometric cave. We knew it before, but I could prove it as well. Let's go to the other caves. Spider Cave, Lechuguilla Cave, and left-hand tunnel. And this is the signal of Lechuguilla Cave. And this is really typically, so we have a long airflow in one direction, then we have a long airflow in the other direction. And this is an exhaling, so the warm cave air moves out, and then we have an outside signal here. And this definitely doesn't match to Spider Cave and the left-hand tunnel. So very different signal to Lechuguilla Cave. We have a very good match, left-hand tunnel to Spider Cave, but no match between Spider and Lechuguilla. And now let's go to the other cave out of the park, Big Manhole and the Blowhole. So this is the entrance to the Big Manhole. This is the opening to the Big Manhole. And now we have Lechuguilla Cave, another temperature signal and we have the big manhole in blue. And you see, don't look to the real temperatures, but look to the pattern. And the pattern really matches nicely between the two caves. And so for me, this is a really good sign that the big manhole is part of Lechuguilla Cave. And the last one is a blowhole far away over the Black Canyon. And you see the big manhole and the blowhole matches really nicely. And we have more or less the same pattern, typically Lechuguilla here for a longer period. And so bringing this all together, the old studies for me brought me to the conclusion 10 years ago that we have mostly thermal-driven airflow in Carlsbad Cavern. But here at the left-hand area and the lakes area, as well in the New Mexico room area, there is something. There might be barometric airflow, but there might be something different. And we are still working on this. And this is just the conclusion by the temperature measurements. And the next one is, so the connection between Carlsbad and Lechuguilla and the connection here. And I think this is a big cave system. Even the Black Canyon doesn't cut something off. So I think this is a big cave system. We don't know what's going on here, but I'm pretty sure we have no connection between Lechuguilla and Carlsbad Cavern and Spider Cave. So again, thanks to the staff of the Carlsbad Caverns National Park and the BLM. And I switch over to Annika, and I hope it's going smoothly.
Okay. I hope you can see my presentation, Andreas.
Yes.
Great. Okay, then thank you, Andreas. Thank you, Hazel. And hello, everyone from Germany. So in my PhD project, I am focusing on processes inside caves, which are related to air pressure and airflow. And today I would like to share some of my findings about air pressure waves inside Lechuguilla Cave and their significance on the microclimate. But before we can actually look at processes inside the cave, it's very important to understand how air pressure fluctuations on the surface work. And on this slide, you can see a measurement series of 16 days of atmospheric air pressure data. And just for your orientation, each dotted line represents 1 day, and the data is based on measurements with a temporal solution of 10 seconds. In Carlsbad, there are two important processes which influence atmospheric air pressure. The first process are the so-called atmospheric tides. And just like tides at the sea, these are regular semi-diurnal waves with 2 highs and 2 lows per day. So you can see for every day, we have 2 highs and we have 2 lows. But beside these regular small waves, there are also irregular larger pressure systems, which can last for several days and which are related to global atmosphere dynamics. If we look at this measurement, we have 2 periods of rising air pressure, here and here, and we have 2 periods of falling air pressure. And they are not regular, but some are a little bit longer than others. And both of these processes are taking place at the same time, and they are both interfering with each other. And the combination of both then leads to the course of atmospheric air pressure, which you can see in this graph. But now I would like to shift the focus to the cave and see what happens when these pressure waves enter and then travel through Lechuguilla. Therefore, this graph shows you the course of air pressure on the surface. This is the gray line, which you've seen before. And inside Lechuguilla, at the toilet bowl site, which Andreas has talked about before. And this is the red line. And as you can see, both pressure signals look very much different from each other. So that means that the atmospheric pressure waves are not just directly transmitted into the cave, but the cave must somehow act on them and somehow change them. And based on my data, I could identify 3 different processes which take place inside Lechuguilla Cave and which influence and which change the pressure signal. First, there is a smoothing effect inside the cave. As you can see in the graph, all the small short-term changes which are related to the atmospheric tides, they are not transmitted into the cave. So you can see them in the gray line, but you can't see them in the red line at all. And this is due to very high resistance at the airlock and also to frictional losses, both at the airlock and then at the walls inside the cave. And besides the smoothing, we can also see a damping effect, which means that the range of pressure values inside the cave is much smaller than on the surface. You can see this here. The red arrow indicates the pressure range inside the cave, and the gray arrow, the pressure range on the surface. So in other words, inside the cave, the highs are lower and the lows are higher. And the reason for this is that extreme values of air pressure, they correspond to higher proportions of turbulence inside the cave. And turbulence weakens the resulting compensating airflow. And therefore, extreme values of the surface pressure are not transported into the cave. And then the last effect I could identify inside Lechuguilla Cave is a delay of the pressure wave. That means that the pressure signal inside the cave lags behind the pressure signal on the surface. So if you take a look at the graph again, you can see that both the highest points and the lowest points inside the cave are reached later than on the surface. And I applied cross-correlation analysis on my data, and I could find a shift of 24 hours, 42 minutes, and 30 seconds. That means that the atmospheric pressure waves need a little bit more than 1 day to travel from the surface through the airlock down to the toilet bowl site. And at the airlock, they are slowed down, and that's why it takes that long, also that it's not a very long distance. Okay. So if we sum up these findings, then the air pressure inside Lechuguilla differs from the air pressure at the surface in 3 ways. It is smoothed, it is damped, and it's delayed. Okay. So next, I would like to present a comparison to other caves of the region and to show why Lechuguilla Cave stands out and what makes it so special from a climatological point of view. Therefore, I have conducted the exact same measurement for Carlsbad Cavern as well. And you can see the results in this new graph. And just for Lechuguilla, the graph shows the course of surface air pressure as the gray line and the course of air pressure inside Carlsbad Cavern at the gate to left-hand tunnel. That's the red line. And as you can see now, it's actually pretty hard to see the gray line because the 2 courses are so similar. If we go back to the processes we've seen in Lechuguilla and compare them to Carlsbad Caverns, it's a totally different picture. So there is no smoothing, there is no damping, and there is no time delay. But the atmospheric pressure fluctuations from the surface are just directly transmitted into Carlsbad Cavern. In other words, the air pressure waves from the outside enter Carlsbad Caverns that travel all the way down to left-hand tunnel, and during their journey, they are not changed at all. And these findings are also supported by an analysis of the corresponding box plot diagrams, as you can see here. And again, it's very much obvious that inside Lechuguilla, the air pressure changes a lot. So the two box plots really look extremely differently. And then in Carlsbad Cavern, they just look the same, which means that there's hardly anything happening to the pressure waves. So what makes these two caves so different? Why do they behave so differently? The first important point is the opening to the caves. Lechuguilla is sealed by a narrow airlock, and Carlsbad Cavern, on the other hand, has this large natural entrance you can see in the picture. So if you think about air pressure waves, it's just much easier to enter Carlsbad Cavern through the large opening than to somehow squeeze through the narrow airlock. And the second important difference is the size of both caves, because Lechuguilla has a much larger volume than Carlsbad Cavern, which means that pressure adjustments inside Lechuguilla just take much longer because there is more air to be changed. And the general rule is that the smaller the opening area to cave volume ratio, the larger the changes on air pressure waves. And Lechuguilla Cave, with a very narrow and tight airlock, but the huge volume behind, is an outstanding example of a cave with a really tiny opening to volume ratio. And that is what we can see in the pressure data.
5 minutes.
Okay, so if we go to Spider Cave, the behavior of the pressure waves is very different again, because here we have times when the outside pressure is rising. You can see this shown by the green arrow. The pressure signal inside the cave runs ahead of the outside pressure signal. So it's not just transmitted, it's not lagging behind, but it's something new. And there must be some different processes acting on the pressure waves there, which we don't understand yet, but which we will investigate. Okay, but now going back to Lechuguilla, why is all of this important? The changes I described before, if you remember the smoothing, the damping, and the delay, they lead to pressure gradients between Lechuguilla and the outside atmosphere. And these gradients here are shown as the light blue area in this graph. And the gradient can be positive every time when the gray surface line lies above the red Lechuguilla line, or it can be negative, just vice versa, when the Lechuguilla line lies above the surface line. But there are only very few moments when the pressure values are equal and when there is no gradient. And every time we have a gradient between the surface and the cave, then compensating air currents are induced. And the very basic concept behind this is that air always flows from areas of high pressure to areas of low pressure. And that is exactly what's happening in the cave as well. So every time the pressure on the surface is larger than inside the cave, the air will flow into Lechuguilla, and vice versa. When the air inside the cave, the pressure is higher, then the air will flow out. And this compensating airflow can be very strong, and it can last several days. And that is what is called barometric airflow that Andreas has also talked about before. And probably every one of you who has been to Lechuguilla has experienced this strong barometric airflow at the entrance to the cave. But it's not only quite impressive when you feel it, but it's also really fundamental and important for almost all aspects of the cave's climate system, including the distribution of temperature, humidity, the CO2 dynamics, and then consequently also for the management, the ecosystem, and the conservation of the cave. Because all these things really are closely related to the airflow and therefore to the effects on the pressure systems. And now as I come to the end, I would like to thank everybody who has supported me during my research in Carlsbad. And I would also like to thank you for your attention. And I think both Andreas and we are looking forward to the discussion and to your questions.